Okay. Hi, everybody. A very good evening. I hope everybody's doing great, right? Christmas is nearing by and your New Year is nearing by, right? I hope you have your plans, right? Are you guys going somewhere? I'm going to Kodaikanal for this thing. What is that? New Year. Are you guys going somewhere for New Year, Christmas, or only in home celebrating? Okay. Fine.
No, sir.
Yes, Kana, tell me. Okay, right. So let me show. I think we have only very less number of people today. Only 6 of you are there. Right? So maybe rather than going for 2 hours, maybe we'll try to wind it up a little sooner, right? And guys, before we start, can someone send me the assignment which you have got? Can someone WhatsApp me? Right. But before that, I have to complete just 2 or 3 more reactions, which are very little important, and then we'll move on to that discussion, right? Right. So before the time, you can just take a while and send me, any one of you, please send me your assignment, which we'll discuss. Okay. Right. So we have completed almost everything, right? Maybe we'll just do the conversions required for the electrophilic substitutions, right? For in benzene ring, we saw so many things: electron donating groups, ortho para directing group, meta directing group, activating group, deactivating group. What are the exceptions there, right? So generally, activating groups are ortho para directing group, and deactivating groups are meta directing groups, right? And exception is only going to be for chlorine, right? Chlorine is actually electron donating group by resonance. It is actually deactivating, okay, but it is going to be ortho para directing. So those are stuff which we saw. Anyways. So if I have to give you this conversion, we have benzene, okay, and I have to convert it into, or let me write it instead of writing it like this, so you'll get familiar with the terms, right? So I want to convert benzene to meta chloro nitro benzene, okay, right? So I want to convert benzene to meta-chloro-nitro-benzene, right? Do it. And you can send me in WhatsApp. I can check. Yeah. So the reaction will happen in 2 steps.
Sir, I have a doubt.
Yeah, tell me.
Sir, chlorine is meta directing or ortho and para directing?
Chlorine is ortho para directing. That's what we told. Chlorine is a deactivating group. It is going to be less reactive than benzene, right? But still, it is going to be ortho para directing.
Sir, so meta chloro nitro benzene means chlorine should be at meta position, or nitro group should be at meta position.
How I will see it is chlorine and nitro group should be meta to each other. Very simple, right? Only 2 groups are there, right? So you have to talk with respect to both of them. Chlorine should be meta to nitro, and nitro should be meta to chlorine. That's it, as simple as that, right? See, if I give you the structures, it's pretty easy, people. Say I can give you the structure: benzene, meta chloro nitro benzene. How will we write? Cl here, NO2 here, or this is also same. NO2 here, Cl here. It is exactly same, right? 1, 2, 3, 1, 2, 3. Doesn't matter, right? 1 and 3 positions should be occupied in the benzene ring. Then that is meta. Both of these are meta.
Sir, shall I say?
Yeah, tell me. Yeah, tell me.
First, concentrated HNO3 with concentrated H2SO4.
Okay, concentrated H2SO4 and concentrated HNO3. Okay, so now we'll get what?
NO2.
Yeah, we'll get nitrobenzene. This is nitrobenzene, right? Now to this nitrobenzene, what should we do?
Sir, we have to add Cl2 in presence of some Lewis acid.
Yeah, Cl2 in the presence of AlCl3, right? Now NO2 is a meta directing group, right? So the incoming nucleophile Cl plus will go to the meta position only, people, right? So we will turn this, okay, we'll write this as NO2 and Cl in the meta position. That's 2 steps. You'll be able to complete this.
Sir,
Yeah, tell me.
sir, what if we do the opposite? First chlorine
Exactly.
and then...
That's a good question. So if we do the opposite, that is, now what are we doing first? We are doing nitration first, right? And then we are going for chlorination. What if I do chlorination first and then go for nitration? This is what will happen, right? Now look at this. When we have benzene, now say I go for Cl2 in the presence of AlCl3, right? Now we'll get chlorobenzene, not an issue, right? Now if I go for nitration, people, H2SO4 plus HNO3, now we'll be getting, now this is an ortho-para directing group. So we will get NO2 at ortho position or at para position like this. I mean, this is ortho, and this is para, right? These two are the products which will be getting, not meta. I mean, meta you will get, but that's not a major product. These two are the major products, right? So if at all you want meta nitrobenzene to be there, first you have to put the meta directing group, that is nitro here, and then go for the next reaction. Yes, understood?
Yes, sir.
Yes, sir.
Right, good. Say, so if I asked you, if at all I wanted benzene to be converted into para chloronitrobenzene, then you would have done this. Okay, or ortho, whatever is going to be the same. Right? Say one more question. Say, I want to convert benzene to say para or I'll write ortho nitrotoluene. Okay, I want to convert benzene into ortho nitrotoluene. And second thing I want to do is I want to convert this benzene into meta nitro how do I put it? Okay, I'll not give you the name. Maybe I want to convert this into NO2, or I want to convert this into C double bond OCH3, and I want to get chlorine in the para position.
Sir, the first one, we have to add CH3Cl in presence of anhydroClCl3, and then we can
go for
nitro. Yes, sir.
That's it, right? So first step, people, now you have understand that we have to get ortho first. So we have to put the ortho para directing group first. Then what is toluene? Toluene is C6H5CH3, benzene ring with CH3. And how do you do it? Friedel-Crafts alkylation. That would be CH3Cl, for example, in the presence of AlCl3. Now what will happen? All you will get is CH3 here, toluene. This is what is toluene. I mean, the U is not there. Okay, now to this toluene you go for nitrating mixture, that is HNO3 plus H2SO4, right? And now I know this is going to be an ortho para directing group CH3. So we are getting, or asking for ortho, so we'll put only ortho, very simple. So we will have CH3 and in ortho position, one nitro group. Okay, right? Fine. Now, say if I want to do this conversion, again, very simple. Yeah, tell me.
Sir, can we do conversion from benzene to meta-nitrotoluene?
Meta-nitrotoluene, yes. You just have to do my nitration first and then go for Friedel-Crafts alkylation. That's it.
Okay, okay,
Understood.
sir.
Sir,
Right.
in the second question, we have to first add Cl, right?
Yeah, first add Cl, yes. Because again, chlorine is going to be the one which is going to be ortho-para directing. This is going to be an ortho. Yeah, this is going to be a para, right? But I know this is a meta-directing group. Right, this is meta-directing, right? If you put this one first, that is, we go for Friedel-Crafts acylation first, right? Then you will get chlorine in the meta position. But all I want is now para, right? So I will go for chlorine first and then going for acylation. How do you do acylation? We'll just do all of this. So we have to do chlorine in the presence of FeCl3 or FeBr or AlCl3, whatever it is. Okay, right? So now all that you're going to get is chlorobenzene. And then now we go for, say, acylation. Now what I have had here, acid chloride, right? CH3COCl, right? Now all that we have AlCl3. So what is going to happen? Now this is an ortho-para-directing group, this one. So we will get C double bond O CH3 like this. That's it. This is what we want. Okay, people, right? Very, very simple questions. All that you have to understand is what are the ortho-para-directing groups, what are the meta-directing groups, and what are the reagents you have to add. Right? That is again more important, right? Just because you know that ortho-para-directing, okay, this is ortho-para-directing, this is meta-directing, but you don't know how to do the reaction. You don't know what is the reagent used. Then again, there's no use in knowing which is ortho-para-directing or meta-directing. Right? So everything is important. Right? Okay, people.
Sir?
Yeah, tell me.
I have one doubt, sir. Why in Friedel-Crafts acylation there is no carbocation rearrangement?
Carbocation rearrangement.
Yes, sir.
Okay, right. See, what I'm trying to understand is, say for example, if I go for Friedel-Crafts acylation, I have the CH3COCl reacting with AlCl3, heterolytic cleavage to form AlCl4 minus, plus the carbocation. Okay, fine, carbocation formed is this. Right now, what you have to understand is, see, rearrangement will happen. See, for those of you who doesn't know what rearrangement is, right? Carbocation can change itself. Say one carbocation can convert itself into another carbocation. Okay, and only carbocation has a special ability. Okay, no carbon cannot do it. Free radicals cannot do it. But carbocations have a special ability to undergo rearrangement to convert themselves into another carbocation. Right now, please understand that can happen. That can happen if there can be a possibility of a more stable carbocation. What I'm trying to tell you is, say there is a carbocation which can be converted into a more stable carbocation. That rearrangement will happen. Right. So if at all we have almost the same stability or say lesser stability, if at all you're going to go for the new carbocation, then we will not go for the rearrangement. Hope you get that point. So like, I don't want to spend time on this. There are rules you have to follow whenever you go for rearrangement. Say you can do only alkyl shift, or you can go for aryl shift. Alkyl shift, hydrate shift, or you can go for ring expansion. And all those things you will be able to do only from alpha position. I mean, I don't want to perplex you guys. All that I'm telling you is rearrangement is something which is not in a service, but if at all you want to do some research about it, you can do, right? But the rules are very simple. You can go for rearrangement of carbocation only if you can make a more stable carbocation, and you cannot just randomly put something somewhere and make a carbocation. There are again some rules. As I told you, there can be only 3 possibilities. Right, one is alkyl shift, hydrate shift, and ring expansion. Again, there is restriction. You can do all these things only from the alpha position. Be very careful. Okay, right. So to answer your question, why is there? This is the carbocation form here. Okay, so if I want to ask you a question, I mean, if I want to answer your question, in this case, rearrangement will not happen because there is no question of a more stable carbocation. Right, there is no question of a more stable carbocation. That's the reason. But if I go for Friedel-Crafts alkylation, let me take this example. Okay, say I had benzene.
Yes, sir. In alkylation, it will occur.
Yeah, alkylation it is possible. Say for example, if we have CH3, 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 CH2, Cl. For example, if we have this, right? Now, what do we expect? We again AlCl3, right? We expect that CH3, CH3, CH2 plus is what is going to get formed, because this is the one which is having the what is that, Cl, and that will leave carbocation as formed, right? So what product do we expect? We expect this is the one which is going to go and attack the benzene ring, right? So we expect something like this: CH2, CH3, 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 right? But this will not be the major product. The actual major product is CH3, CH3, and CH3. This is what is going to happen. This is the product we actually see. Right now, how do we do it? Is very simple, right? One second. If this moves, I think there's one carbon atom missing, right? Yeah, this is going to be CH2, CH3. Okay. Now, what is going to happen is, now this is your Fine. This is going to be a carbocation. So you'll understand that this methyl group is capable of shifting to this. Okay. And heterolytic cleavage. There's a bond here. Heterolytic cleavage. So what will happen? CH3, C, CH3. Now this carbon has lost electron, so it will get a positive charge. And this CH3 has moved to this donated electron here. So the positive charge is gone. So we would have had CH2, CH3. And this is a more stable carbocation because this is primary. And this would have been tertiary. And there is a possibility. Right? So that will go and attack the benzene ring, and you can understand that this would have been the actual compound form and not this. Okay, but that these all are not there in your syllabus. Okay, maybe if you're gonna prepare for competitive exams, yes, these things are there in your syllabus, right? But right now, whatever I told you, you really don't have to worry about it. Okay.
Okay.
Fine. So that is about the electrophilic substitution reaction, but there are a few more reactions left out as we have already discussed, right? One thing is in preparation of alkenes. I missed a alkynes. Sorry, preparation of alkynes. Right, I missed one reaction. The reaction that I missed is actually before I move on to the reaction. Right, I want to revise one particular type of reaction. Okay, I want to revise nucleophilic substitution reaction. We have already seen electrophilic substitution. Right, electrophilic substitution is one positive charge replaced by another positive charge. Right, now it is the exact opposite. Nucleophilic substitution, one negative charge is going to get replaced by another negative charge. Right, very simple, people. Say for example, if we have CH3Cl, right, and say I have NaOH. Okay, right, I have CH3Cl and I go for NaOH. Right, now from NaOH, obviously aqueous solution it is, right? So we'll obviously get OH minus ions. Okay, now understand that this OH minus ions are more reactive than Cl minus ions. Okay, so what is going to happen is this OH minus will come and attack this particular carbon, and obviously if this oxygen makes a bond with this carbon cannot have more than 4 bonds. Right, so obviously one negative charge has to leave, and that would be Cl minus heterolytic cleavage. Show it like this: first step attacking, second step leaving. As simple as that. So we will get the product as CH3OH. Very, very simple reaction. Right, now this reaction you will study very much in depth in your 12th class, but for now all you have to understand is the introduction. This is the mechanism. Again, mechanism can be of 2 types. Right, one is where I have SN1, SN2. Do not worry about any of that. Now, all you have to understand is what do you mean by nucleophilic substitution? One nucleophile replacing another nucleophile. As simple as that. Okay, right. Now, if the same kind of example, but instead of OH minus, right, I can actually produce any number of n number of nucleophiles. Say I can have Cn minus coming. I can even have, say, a carbanion itself as a carbanion itself as the nucleophile. So n number of nucleophiles are possible. Okay, and one such special nucleophile is this. Right, look at this reaction. We have, say, for example, CH3Cl. Or let me start from first. Right, say I have CH3, CH, not even CH, it is C triple bond CH. Right, now what I want to convert this into is, say, instead of having 3 carbon atoms, I need to have, say, 6 carbon atoms, 7 carbon atoms, 8 carbon atoms. Right, how do I out of nowhere include a carbon atom into this? Okay, what I'm trying to do is basically I want to convert this into something like this. Okay, something like this: CH2, C triple bond CH. How many carbon atoms I have it? Now here I have 3, but here 1, 2, 3, 4, 5, 6 carbon atoms I have, like here 3 more extra carbon atoms are coming. Okay, now how do we do this, people? How do we do this? With the help of nucleophilic substitution reaction. Okay, beautifully we'll be able to do with the help of this particular reaction. What I'm trying to say is that you will be able to increase the chain length. Okay, add carbon atoms to the existing molecule. Okay, very beautiful reaction. We'll try to understand what exactly is happening. Okay, right. Now, if I can have CH3, C triple bond CH, and we already know this is acidic, right? We have already proved for the fact that terminal alkynes are indeed acidic in nature. This hydrogen will be able to come out. We have seen the reasons also. The conjugate base formed is stable because this is an sp hybridized carbon atom, which will pull electron, decrease the negative charge. All those things you have already seen. right? Now, all I'm trying to say is this particular hydrogen is acidic, right? So if I put the base, for example, say, no, it won't react with the base, but if I make it react with Na, metal, right? Now, what is going to happen? We have already seen, right? We are going to form like salt plus hydrogen kind of thing. So C minus Na plus hydrogen gas is evolved. That is very simple. Okay, now we understand that I already have 3 carbon atoms. Now all I need is 3 more carbon atoms, right? 3 more carbon atoms is all we need, isn't it? So people, if I had say CH2, okay, fine. No, 1 second. Or I'll write like this: CH3, CH2, CH2, Cl. Now I have this compound, right? I need 3 more carbon atoms, right? Okay. Now I took the 3 more carbon atoms and a chlorine. Now I am going to have the nucleophilic substitution reaction happening beautifully. How? Now this is the negative charge. People forget about Na plus. What happened last time? OH minus was the nucleophile attacking the carbon having the chlorine and the bond broke. Right? Same way here, this carbon is having the negative charge. It will come and attack the carbon atom which is having the chlorine, and the Cl minus will be. Very, very, very simple reaction. Okay. Now what is going to happen? Can I write the compound like this? See, but I don't think the compound you will be able to get it like this exactly, but you will understand that there are going to be more carbon atoms. Okay. So this is, we start with this, say this CH3, C triple bond C. Okay. It is there. And that is attached to what? It is attached to this particular carbon atom, right? CH2, CH2, CH3. Okay. So, I mean, this is not the exact conversion I wanted to do. Say I want to convert this to this, right? This is how I do the conversion. Okay. So at the end of the day, what you have to understand is here we are increasing the number of carbon atoms, right? From 3 carbon atoms, you can actually go to any number of carbon atoms. Right? I mean, obviously too much higher number, I don't know, like the yield of the reaction will be very poor, but say after 10 carbon atoms, you can easily do this. Okay. Now, I hope yeah, go on.
Could you repeat the last step? Like why?
Yeah, last step. So now we understood that this is acidic. So we would have formed CH3, C triple bond C, C minus Na plus. Right? Now this particular reaction, what is going to happen here is your nucleophilic substitution reaction. One nucleophile replacing another nucleophile. Now this is the nucleophile coming. CH3, C triple bond C minus is the nucleophile. Now that negative charge carbon is going to attack the carbon having the chlorine or having the functional group. I would say in this case having the halogen. Right? Now if this attacks, this carbon cannot have more than 4 bonds. Right? So obviously one of the bond has to break, and the double this obviously is the bond which will break like the heterolytic cleavage. Gone. So you just have to join this carbon atom and this carbon atom and write this product. Very simple.
Sir, but yes, how can it replace Cl? Cl is more electronegative, right?
It's not about electronegativity here. Okay. So there is this term called as nucleophilicity. Okay. There is this term called as nucleophilicity. Nucleophilicity is nothing but the strength of the nucleophile. How do you have reactives like sodium is more reactive than magnesium, something like that. This is about the reactivity of the nucleophile, strength of the nucleophile. Okay. Now what you have to understand is, again, I don't want to go into detail as such. All you have to understand is the nucleophilicity of say C triple bond C minus is greater than that of Cl minus or B or Br minus or I minus or F minus for that matter. Okay, all that you have to understand. How do we decide the nucleophilicities? Actually, there are again simple logic you'll be able to analyze and you'll be able to decide it. Okay, maybe we'll have a special class for that. Nucleophilicity, the rearrangement in carbocations, how it is going to happen. For all this stuff, we'll actually have a special class, right? But for now, all you have to understand is the strength of nucleophile. That the term which you have to use is nucleophilicity of the alkene negative charge is going to be greater than that of Cl minus or Br minus or I minus or F minus. Okay, and that is why the replacement can happen. All right. Okay, and for your question, yes, it is not based on electronegativity. Okay, actually, a more electronegative element will be less nucleophilic. Right now, at least that point, I'll try to explain you how. Right, see, what is a nucleophile first? Right, a nucleophile is there. If at all I have a positive center, now it will have say 2 electrons in the form of this. It has to donate these 2 electrons to the positive center, isn't it? Right, it has to donate this 2 electrons to the positive center. So if at all this element is highly electronegative, right? It will hold on to the it will hold on to its own electron like very strongly, right? Again, I repeat. And for nucleophile, it has to donate its electron pair to some other species, right? That is what is a nucleophile. Okay, right. Now, if at all I want to donate the lone pair, and if I find that the nucleophile has an element which is very highly electronegative, now what will happen? It will not let these electrons go because it is very highly electronegative. It has very high affinity for electrons, right? So the ability to donate the lone pair is actually getting decreased. By that, I can say that the nucleophilicity is also decreased. It is all about how much ability that particular species has to donate some electrons to the next one. If it is highly electronegative, strongly held, it will not be able to donate that efficiently as in the case of a less electronegative element. Okay, I hope that makes sense to you.
Yes, sir.
Right, good, fine. So this is one reaction. Again, say if at all we want to have more examples, we can have people say, if I ask you, I have, no, this won't work. Say I have CH3, C triple bond. Okay, why again this one? Say I have CH triple bond CH. Okay, now I go for 2 moles of sodium. Okay, but 2 moles of sodium will be too much, right? No, actually we'll take only 1 mole of sodium because again both the hydrogens are acidic, but only 1 mole will take. 1 sodium only will take. Okay, and after that, say it forms a compound A, right? And this is going to react with say this one to form B, right? Can you find the structure of B?
Sir, it'll be a cyclohexane with the C carbon bond attached to it and a triple bond CH.
Yeah, correct. So this A would have been very simple. Say you have to remove only one of the hydrogens, even if the both hydrogens are acidic. In this case, we're using only one Na, 1 mole of Na, 1 mole of this and 1 mole of this. So we'll remove only one of the hydrogens, right? Now this is the negative charge nucleophile. Now that has to attack the carbon atom having the chlorine. Please understand, this is the carbon atom having chlorine, this is the carbon atom, and this bond has to break. Very simple, right? So we easily have a cyclohexyl ring with this carbon having C triple bond CH. Now this is your product. Very, very simple reactions. Okay, people. Right, I think any kind of question given to you, all that understand is make the carbanion and make it attack the carbon having the nucleophile, I mean having the chlorine, and make the chlorine leave. As simple as that. Okay, I hope you all of you are able to follow. Right, so this is one reaction.
Final product?
This is the final product B.
Okay, so what happens to Na plus?
Nothing. Na plus and Cl minus will go as NaCl. We have Na plus, Cl minus coming, NaCl as a side product.
Okay.
Okay. Right. Fine. So that is about this reaction which I missed. Right. Another reaction is again preparation of alkanes only. Right. Now preparation of alkanes from alkyl halides. Okay. Preparation of alkanes from alkyl halides. Excuse me. Right, now how are we going to do this? Now this is where our Woods reaction will come into the picture. I think this is the first name reaction I think you're seeing. Is it not? Right? This is name. Friedel-Crafts is another name which you have seen, right? Friedel-Crafts. Again, Friedel and Kraft are the 2 scientists who discovered that reaction. So they gave the reaction their name. Same way, Woods was the scientist behind this particular reaction we are going to see. So we'll name it after him. Right? See, people, they will just give you the reaction in the exam and they will not even tell you that it's Woods reaction. Right? Or they will just tell you Woods reaction and they will not tell you what exactly is happening, what reagent you will add. Right? So you should know both of them. What is Woods reaction? What is happening in the Woods reaction? What is the product? What is the reagent? What is the reactant? Everything we should know for any name reaction for that matter. In 11th, it is very easy because you will have only a handful of name reactions. But in 12th, you at least have 30 to 35 name reactions. Okay, right? So be prepared for 12th now itself. Every name reaction, put a notebook, like now itself you start. Okay, put a separate notebook for only named reactions and their mechanisms and their products. Okay, it will actually be very useful. Fine. So in which reaction, what is going to happen? We'll try to understand. Right. So as I told you, we are going to prepare alkanes from alkyl halides. Okay, prepare alkanes from alkyl halides. Okay, and the beauty of the reaction, you know, is what? Right? You will be able to prepare, right, alkanes only with even number of carbon atoms. Strange, right? You will be able to prepare alkanes, no doubt about it, right? From alkyl halides, yes, right? But you will be able to prepare alkanes only with even number of carbon atoms, 3, 4 carbon atoms, 6 carbon atoms, 8 carbon atoms. You can never, ever prepare 7 carbon atoms or say 5 carbon atoms with alkane with the help of your Woods reaction. It's not possible. You'll understand why. Okay, so this is a specialty. Say if I tell you, we don't even have to go for the reaction as such, but I'll tell you, say option A, CH3, CH2, CH2, CH3. Option B, CH2, CH, CH3, CH3. No, this is also not possible, I guess. Right? Say CH2, CH3, and say CH3, CH, CH3, CH, CH3, CH3, and say the next last one. Say I have CH2, CH3, CH3. And if I ask you, with respect to which reaction, which alkane cannot be prepared, you can just blindly tell that B is the answer. Because if you check for all the other ones, 4 carbon atoms, 6 carbon atoms, 2 carbon atoms, everything is even number. But this one has only 3 carbon atoms, which cannot be prepared by Woods reaction. You can just blindly say this. Okay, this kind of question can also be asked. Right? Okay, people. How are you going to do this? Right now, let us give you the general reaction first. Say again, we are going to prepare it from alkyl halides. So it is Rx, right? And to this Rx, we are going to add sodium. Okay, we are going to add sodium in the presence of dry ether, or I think it's acetone. Sodium in the presence of acetone. Right now, don't worry about acetone. Acetone is just a solvent here. Okay, acetone, generally we use water as solvent, but for some of the reactions we use organic solvents also. Acetone is what? Acetone is nothing but CH3, C double bond O, CH3. This is nothing but a solvent, as I told you. Okay, it has no role to play in the reaction as such, except that it is going to be the solvent, that is Rx and sodium are dissolved in this particular solvent only, acetone. Okay, so what is going to happen here is, people, right? So we are going now, how many ever number of carbon atoms you have in the alkyl halide, right? You are actually going to double it. Okay, now how will I write the product? Look at this, R. So we have to use 2 moles of Rx, 2 moles of sodium to form RR, combining together, 1 alkyl group, another alkyl combining together, and what will be formed is another 2 moles of NaX, say 2 moles of NaCl, 2 moles of NaBr, depending on what is the halogen present here. Okay, guys, just give me 1 minute and I'll be back. Just give me a moment. I'll be back. Okay, sorry guys. So yeah, what I was trying to say is that whatever is the number of carbon atoms here, right, you will always double the number of carbon atoms when you go to the product alkane. Okay, right? So for example, people, if I start with simple CH3Cl, 2 moles of this, and I add 2 moles of Na in the presence of acetone, okay, what did I tell? You are going to form 2 moles of NaCl. That is very simple. 2 Na, 2 Cl gone. So what I have to do? Whatever is here, just double it. CH3, CH3. This would be the alkane form, ethane. Right? So you start with chloromethane, right? And you are going to end up with ethane, double the number of carbon atoms. Say for example, if I asked you 2 moles of say CH3, CHCl, CH3, right? And then again 2 moles of Na in the presence of acetone. Now you, in these kind of questions, you have to be very careful. Okay, whichever carbon atom is having the halogen, you have to double it there only. Okay, so maybe if I write the product, you'll understand what I'm trying to say. So if I write the product of this should look like this: CH3, CH, CH3. Right now, this carbon is the one which is having the chlorine. So this carbon is the one, again, the same carbon is the one which is going to have the chlorine. Those 2 carbons should be attached to each other. Right? Say again, I'll have CH3, CH3 like this. And how do we properly write this? Maybe we can take this as the main chain. This as the main chain, for example. How do we write this properly? CH3, CH, CH3, CH3, CH, CH3. Again, what is the next one? CH, CH3. This is this one. And again, one more CH3. This is how we write this. Okay. Now, if at all I want to make the little more things simpler, say if I start with CH3, 1 second, CH3, CH2, Cl, and I go for 2 moles of sodium in the presence of acetone. Right, again, you see that this is the carbon atom having the chlorine. So this is where doubling should happen. So you will form CH3, CH2, again start CH2, CH3. I hope everybody, yes, what are the doubts, Suprajit?
So not a doubt, sir. In Wirth's reaction, I think in textbook it's a dry ether, sir, the solvent.
Okay, acetone, where do we use? Acetone. Okay, my bad. Maybe it is in the presence of Grignard reagent. Please change it, people. Right? Please change it. This is not acetone. Okay, it is dry ether. That is what I first wrote. But what's happening? Okay, anyways, that's what I first wrote. But I think some messed up thing happened. So sodium in the presence of dry ether. Okay, I'll just change all of these to dry ethers. So I hope everybody is understanding what is happening here. Wherever the carbon atom is having the chlorine, that part you have to get it doubled. Say if I ask you, for example, 2 moles of not benzene. Benzene is not possible. 2 moles. Me and my diagrams, never ending story. Okay. Say I have 2 moles of this one, right? And if I ask you, what is the product? Dry ether, sodium in the presence of dry ether. Can just sketch the product quickly, people. Quick.
Sir, it is another cyclohexane ring connect where the carbon atom is connected.
Right, this one will have connection with another cyclohexane ring. That's it. This is the answer. Right, this is where the chlorine is. Double it in this carbon. That's it. Make another cyclohexane ring. That's it. Plus 2 NaCl. Very simple. Right. Okay. Now the next question is, what is the mechanism? Right. We understood. Okay, doubling will happen. How do you make the product? Everything we understood. But obviously, I don't know the mechanism also, isn't it? I don't know whether the mechanism is there in your book, but we will see the mechanism because it's going to be free radical mechanism. Wonderful reaction, right? Fine. So the mechanism of this reaction. Right. So the mechanism is very simple, people. So we have Rx. Now, please understand, sodium is already a radical. Okay. Sodium is already a radical. How sodium is a radical? Look at this. 1s2, 2s2, 2p6, 3s1. This is the configuration, right? Now, how do you generally define a radical? You define a radical in such a way that it has an unpaired electron present. Now look at this. In 2p6, all the electrons are paired. But if I go to this 3s1, you understand that it's actually having one unpaired electron. right? So sodium, I can represent it like this, or I can just represent sodium as a sodium radical. That is also completely all right because it is having an unpaired electron. Okay, right. So now what is going to happen? This sodium radical is going to react with this molecule so that this bond undergoes homolytic cleavage. Okay, and obviously I have to use 2 moles of this, 2 moles of this, 2 moles of this. Okay, anyways, what is left out from this? What will be left out is 2 R dots, okay, plus 2 X dots plus 2 Na dots. Now these two will easily combine to form NaX, 2 NaX, right? And these two, how do we write this? R dot and another R dot will come together to form R. Very, 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 very simple. Right? If I have to tell you in the terms of reaction, it's very simple. CH3Cl, for example, right? Na dot. I write 2 moles of Na dot, 2 moles of this. So we will be getting 2 moles of CH3 dot plus 2 moles of NaX, NaCl. That we directly write. 2 Na, 2 Cl dot. This is the homolytic cleavage. Right? So now what is going to happen? I have one CH3 dot. We have another CH3 dot coming together to make a bond. Done. Very, very simple. Okay, right. Now, if I can little up the notch, okay, but again, this is not in a syllabus. These kind of questions you're not going to get just to get the fun out of it. Okay, if I ask you, okay, I have dye this thing. Okay, in the same compound itself, I have 2 things. Okay, and I go for 2 moles of sodium in the presence of dry ether. Right, predict the product. Okay, now fine, you do it.
So 2 moles of the compound is there, right?
That is one of the products we definitely can expect, isn't it? Say we can actually expect the product like this. Something like this you can expect, right? Say here one radical will be there, here one radical will be there. Again, it can happen, right? But if you see, again, the thing about organic chemistry is that the mechanism, obviously we understood, right? Now, if at all through the same mechanism, if we can form multiple products, right? Same mechanism only, but if you can form multiple products, the product will be so chosen in such a way that there is minimum energy expenditure. Okay, so like again, I repeat, right? So if at all you can form multiple products with the same mechanism, okay, the product will be formed in such a way that the energy spent is minimum, right? So what I understanding here is that, say we formed one free radical and another free radical. Now they both have to attack each other to make this kind of things, right? But here, what you need to understand is that, say if this bond undergoes homolytic cleavage, right? What will be the radical form? One radical here, another radical here, right? Now, instead of this attacking another mole of this, what will happen? This will come together, and the product is actually the suspense, right? So the product will be like this. Okay, right? These kind of interesting shapes of molecules you can make, right, with the help of this reaction. Anyways, don't worry about this, right? Just know the fun part of it. Like this also you can make, right? But for your level, all these kind of questions will be asked. Normal questions. Okay, right? So that is about Wood's reaction. Again, the beauty of the reaction is that if at all again you have only monochlorides, you will be able to go for doubling the number of carbon atoms. That is why we say even number of carbon atoms can only be produced. Right? If at all I have only one carbon atom in the alkyl chain, alkyl halide, then I form 2 alkane with 2 carbon atoms. If at all I have 3, I go for 6. If I go for 5, I go for 10, doubling. So anyways, you multiply by 2. So always you will get alkanes only with even number of carbon atoms. Okay, right? Fine. Now, another very, 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 very similar reaction to this, right? Exactly the same thing is going to happen. Radical will be produced and the 2 moles of the radical will combine together to make a double, let's say the number of carbon atoms will be doubled. Same reaction we are going to see, except that the functional group is different. Okay. Now, that reaction, what we are going to see is nothing but your Kolb's decarboxylation, we call it. Okay. Now this is similar to Woods reaction in terms of the mechanism, right? Free radical mechanism it is. And here the another similarity is that here also we are going to have double the number of carbon atoms formed compared to the reactant. Reactant has three means the product will have 6 carbon. 4 means 8 carbons, things like that. Okay. Decarboxylation. Okay, right. So this term decarboxylation is very interesting. Okay, right. What do you mean by this? This means removal of CO2. That's what it means. Decarboxylation, plainly, bluntly, means nothing but it is going to be a reaction in which there is going to be CO2 removed from the molecule. Okay, CO2 removed from the molecule, as simple as that. Okay, so what is going to happen here? Right. So what I'm trying to tell you, for example, say if we have RCOOH, okay, obviously first you have to make the carboxylate ion first. We have to, this has to react with NaOH. I know acid-base reaction is going to happen. That's very simple, right? So what will we form? We will form RCOO minus and Na plus, right? And obviously water molecule is produced. This reaction is very simple, acid-base reaction. Okay. Right. Now, people, when I go for electrolysis, it is also called as Kolb's electrolytic decomposition. Okay, because we are going to use electricity here. Okay, this is going to happen in terms of with the help of electricity. That is why it is called as Kolb's electrolytic decomposition. Now, it is also called as Kolb's electrolysis. All reactions means the same. Kolb's electrolysis, Kolb's decarboxylation, Kolb's electrolytic decomposition, all the names refer to the same reaction. Okay, right. So now here what is going to happen is, people, right? Now I don't want to go into the details of how exactly you're using the electricity, right? But we know electricity is nothing but flow of electrons. That at least we know, isn't it? Electricity is nothing but flow of electron. Correct. So what I'm going to do is that I am going to pass electricity through this compound, or say something like that, such that from this 1 electron is removed. Okay, from this 1 electron is removed. Okay, right. So now we have to use 2 moles of the same compound. Okay, so here we will use 2 moles of this particular carboxylate anion. Okay, again write it like this: carboxylate anion is there. Okay, right. Now 2 moles of this. So I have to actually remove 2 electrons, 1 from each. Okay, 1 from each. Now we have to understand this very carefully. Okay, so people, we have RC double bond O and O minus, right? O minus means what? I already have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are already there on this carbon. Oxygen. Okay, 8 electrons are already there on this oxygen. No electrons are unpaired. Okay, so from this, if I just remove 1 electron, removing 1 electron, minus 1 electron, right? So negative charge is gone, definitely. Right, and say this was a lone pair initially. From this only 1 electron is removed. Can I tell this electron will become unpaired? Right, so negative charge is gone, right, because I'm removing 1 electron, and also one of the electron is becoming unpaired. All of them are paired now. 8 electrons are there, 4 lone pairs. Right, so if at all 8 electrons, no problem. Now if I remove 1 electron, first thing, negative charge is gone. Second thing, one of the electron is going to become unpaired. So can I indirectly say that you are trying to convert a negative charge into a free radical? Again, I repeat, by removing 1 electron from this, negative charge is gone. Neutral species. Okay. Second thing, by removing 1 electron, one of the electron is going to become unpaired. So what are free radicals now? They are neutral species. They are not charged. They are neutral species having at least one, not at least one, only 1 unpaired electrons. Okay. So I am going to write this molecule as RCOO dot, as simple as that. Okay, so from a carboxylate ion, you remove 1 electron, we are going to end with carboxylate radical. Okay, from the carboxylate anion, you remove 1 electron to form carboxylate radical. Okay, so can I tell here that here we are going to have 2 moles of RCOO dot. Okay, 2 moles of RCOO dot is what I have. Right, fine. Now let us write the structure of this. Okay, now if I write the structure of this, RC double bond O dot, no issues. Okay, right. Now what I'm going to do is that I am going to remove CO2. What is CO2 structure, people? CO2 structure is this. We are going for decarboxylation. CO2 is what? C double bond O, double bond O. All right. Okay. So now please understand that somehow we have to remove this part. I don't want to mark it. Somehow you have to remove the CO2 part, right? But you have to have a double bond. Now you have only single bond between this carbon and this oxygen, right? So all that I can think of is if this bond, what I'm marking, is actually undergoing homolytic cleavage. Right, let me show it. Homolytic cleavage. So can I tell we would have formed R dot plus C double bond O, one dot, and oxygen having another dot. Now what is going to happen? This is going to come out. So to form CO2. Nothing. I say I should not be showing this step. You know what should I do? I should actually show this happening, and you have to show the bond formation directly. That's it. To form CO2 molecule, and what is left out, people? What is left out is R dot. And how many such R dots? So I will directly write 2 CO2. I'll just write minus 2 CO2, not even minus 2 CO2. We understand how is it happening, right? I'll again show you. Look at this. R, or let me write it here. Okay. So we have R, C double bond O, O dot. Okay. Now this bond undergoing homolytic cleavage. So this is going to come here, and this bond is also going to undergo homolytic cleavage. So I'll directly write minus CO2 to form R dot. Very, very simple. Okay. Now exactly same thing what is going to happen in the case of Woods reaction. So you formed how many R dots now? You form 2 R dots. So instead of writing, I can write it like this: R dot and another R dot coming together to make R. This is your final product. Okay, this is your final product. Okay, let us come from first. What exactly is happening by try to see. So we have taken carboxylic acid. So this is like a preparation of alkanes from carboxylic acids, from acids. Okay, that's actually the heading, and under that heading we have Kolb's electrolysis. Okay, and I think we have one more reaction also. Fine, we'll see that anyways. So we have in Kolb's reaction, what is going to happen? We take 2 moles of the acid, react with first the base. So we are going to form the carboxylate anion. Okay, so we are taking 2, but if I talk about only 1 carboxylate anion, from that I just remove 1 electron. Okay, so 2 carboxylate ion means 2 electrons, so I'll remove to form carboxylate free radical. We understood how the free radical is getting formed. Okay, now this free radical is going to get formed, and after that what is going to happen? Carbon dioxide molecule is going to come out, and we understood how the mechanism is also. Like first this one undergoes homolytic cleavage, a dot here, again making the bond to form CO2. Very, very simple, right? You should not be actually showing this step. Okay, you should not show the radical here. Directly show the bond making here, and CO2 is getting eliminated. Right? So if CO2 is getting eliminated, what is remaining is as R dot, and 2 such R dots are here. So exactly like Woods reaction, R dot will combine together to form RR. That is your final product. So again, people, we will be able to double the number of carbon atoms, whatever was there in the carboxylic acid, but except that 1 carbon atom is gone. Why? Because 1 carbon atom is going out as CO2. Be very careful, right? Okay. So I can tell that if at all I had, say 3 carbon atoms in the carboxylic acid. Okay. Now all I would have done is that I would have actually formed 4 carbon atoms in the final product. For example, and what I'm trying to tell you is, look at this. Say we started with CH3, CH2, COOH. Right? Now first I'll make it react with NaOH. So to form CH3, COO minus Na plus. Right? Now again 2 moles of this, no issues. Right? 2 moles of this, no issues. So from this 2 electrons are removed. Right? From this minus 2 electrons. Okay, minus 2 electrons are removed. So what will happen? It is going to form 2 moles of CH3, COO dot. Okay, from this we will remove 2 CO, no, CH3, CO dot, no, I've missed 1 carbon atom here. Okay, so we are going to form CH3, CH2, COO minus Na plus. Done. So from this 2 electrons are removed to form CH3, CH2, COO dot. Right, and from this 2 carbon atoms in 2 CO2 molecules are removed. We know the mechanism how is it removing. right? So to form 2 moles of CH3, CH2 dot. And this one, how do we write? We write this as CH3, CH2 dot, again, CH2 dot, CH3, right? Now this will combine together to form CH3, CH2, CH2, CH3. That's what I told. Now look at this initially. 3 carbon atoms I had. Now it became how many carbon atoms in the product with alkane? 4 carbon atoms. 3 became 4. Right? So if I ask you, if I had 4 carbon atoms in the carboxylic acid, how many carbon atoms will be there in the alkane formed through Kolb's decarboxylation? Again, I repeat the question. How many carbon atoms will be there in the alkane if initially I had 3 carbon atoms in the carboxylic acid during your Kolb's decarboxylation reaction? Think about it and tell me the answer. Or if I directly give you this CH3, CH2, CH2, COOH, okay, and we go for Kolb's. I'll just tell that electrolysis. I'll just tell this. That's it. Nothing I'll tell. Okay, electrolysis, obviously the presence of NaOH, all these things will be there. What should be the final product? Right.
Sir, 6 carbon atoms.
Yes. All that you have to understand is this COOH is gone as CO2. Other than that, how many carbon atoms are there? This many carbon atoms, 3 carbon atoms will be there. So you just double them. So you are going to form CH3, CH2, 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 CH3. As simple as that. This getting doubled and this eliminated as CO2. Done. 6 carbon atoms. Okay. I hope everybody is able to follow this. Okay, people. Right? Any questions anybody has? Right? Okay. Now, I don't know if this reaction is also there for you in your syllabus, but there is another decarboxylation, but not through electrolysis, normal decarboxylation. Okay. Right. So this is nothing but decarboxylation through heating. Okay. If you give enough energy, okay, through heating. Mechanism and all is
calcium oxide.
Yeah, calcium oxide, exactly. Heating with okay, actually like this. Heating with calcium oxide.
There, sir, in our portion.
It is there, right? Okay, good. Right, fine. Now here also the mechanism and all is very simple, people, right? But except that, instead of doubling the carbon atom, you will just have 1 carbon atom less. Very simple. Look at this. Let me actually give you the shortcut. You don't have to go to the mechanism and all. I'm going to directly give you the shortcut. Okay, right. So what and all we are going to remove? What all we are going to add? We are going to add NaOH, right, and CaO. Okay, right. Now remember that the side product through in this reaction is always CaCO3. Okay, this reaction is always going to be CaCO3 is the side product. Okay, now how can I remove the CaCO3? Let us try to understand. Or wait. Or let it be, no issues, right? I have CaCO3. Okay, now how can I CaCO3 or Na2CO3? I'm so sorry, it's Na2CO3, right? I'm so sorry, this is going to be right. Na2CO3 is obviously going to be the side product. Okay, Na2CO3, how it will be formed? N1, but how it is 2 NAs? Where 2 NAs came? And
sir, actually there is already like CH3CO minus and Na plus.
I guess that's what you understand, isn't it? CO minus Na plus, and another time I have to go for NaOH. Okay, we'll keep it like that. Okay, and just for understanding. Okay, the mechanism is different, but don't worry about the mechanism for now. Okay, first we'll put NaOH, right? So what will be formed is RCOO minus and Na plus. Now what we'll do is we will go for NaOH and CaO. Now remember this CaO's role, I'll tell you what is the CaO's role, but it is actually going to be only NaOH and we have to heat it, okay? We have to heat it, right? This process is also called as soda-lime process. Okay, lime is nothing but CaO, right? Soda is nothing but NaOH. Okay, it's also called as soda-lime process, right? So first we'll make it react with NaOH, right? And then the salt of the carboxylic acid is formed, acid-base reaction. Now what I'm going to remove is Na2CO3. Now look at how am I removing. Okay, Na1, Na2, carbon, 3 oxygen, 1 oxygen, second oxygen, third oxygen here. That's it. Again, I repeat. All I'm going to remove is Na2CO3. Okay, so first sodium, second sodium, 2 Na is gone, 1 carbon gone, 3 oxygen, 1, 2, and 3 third oxygen is here. Very, very simple. So now what is remaining, people? What is remaining is R, and from this H is remaining, right? So you just make RH plus Na2CO3. This will be the product. Okay, this is what is going to be the product. So again, I repeat. First, you add NaOH to form your RCO minus Na plus. Another NaOH. From this, you remove Na2CO3. Okay, and actually, this CaO's role is actually, what is going to happen in this. You can actually have CaCO3 also getting formed. Right? Why it will happen? Because from this, if you go through the mechanism, again, exactly same mechanism, CO2 will be eliminated. Okay, and this CO2 will react with CaO to form CaCO3. This you have already seen this reaction, lime water turning milky. Right? This is your quick lime. CO2 gas will be passed. You're going to form CaCO3, which is going to form the milky solution. I hope you remember. Right? So the CaO's role is just to absorb the CO2 produced and to make it into CaCO3. That's the role of CaO here. Okay, people. Right. So now, if I go for some example, very, very simple. I hope everybody is following. First acid-base reaction, carboxylate salt. From that, Na2CO3 removed to form your hydrocarbon. Now, how do you do this? For example, if you had CH3, CH2, COOH, first make it react with NaOH to form CH3. What is wrong?
Sir, CH3, CH2.
Yeah, like my eraser is not working. Yeah, so CH3, again same problem. Okay, CH3, CH2, COO minus Na plus. Right, now just put NaOH, right, and CaO and heating. Right, so all you're going to remove is Na2CO3. Right, so what is remaining is CH3, CH2, and a H. That is nothing but CH3, CH3. Plus what is remaining is Na2CO3, and you can have side product also to be CaCO3. No worries at all. But again, you just have to concentrate on this. Okay, this is the product form. So what do you understand? From the carboxylic acid, one carbon atom is less. Okay, because one thing is going as carbonate. Okay, one of the carbon is going as carbon dioxide, basically, right? Eventually, all you have to form is Na2CO3 and CaCO3. Right, so you have to understand that one carbon atom is less compared to the parent carboxylic acid. Okay, people, right? So these are all the reactions which we missed during the preparation part, and I think some reactions also. Right, you can just go through all of them. So now successfully we have completed all the reactions which are given in your textbook. Okay, so maybe we'll now take a break. Okay, time is 7:35 almost, so we'll meet by 7:45. Okay, and then we'll go with the discussion for assignment. Okay, if you guys have any questions, you can ask me. Is there any question anybody wants to ask me?
Sir, can we continue just like that?
Sorry.
Can we continue without a break?
Can we continue without a break? No, actually, I have to take a break. It's 1 hour. I've been continuously talking. Just 10 minutes. You want to go somewhere, Raghav?
Okay, sir, no problem.
No. I'm asking you. You have any plans of going out somewhere?
No, sir.
Okay, right. Just 10 more minutes. Almost 7:35. 10 minutes. We'll take a break. We'll continue. Okay. Rest for you. Rest for me. Rest for everyone. Right. So, guys, just don't go out of the meeting. I'll just mute myself. I'll stop my video. I'll be back in exactly 10 minutes. I'll meet you then. Bye. Okay, people, I hope you're back. Everybody's back. Are you guys back? Shall we start?
Yes, sir.
Right, good. So that is all about this reaction. So let me download that. Just a moment. Let me download that.
Sir, I've sent it.
Yeah, I saw. Yes. Okay, got. Let me share my screen. Okay, people. Oh, first reactions we didn't see again. Fine. This, guys, we just go back. Okay, just a minute. Just one more reaction. There is this that is left out here, and then we'll come back to this. Okay, right, people. We saw ozonolysis, right? Okay, just like ozonolysis, we have this reaction with KMnO4. Okay, so we are going for oxidation reaction, oxidation of alkenes, right? Alkenes with concentrated, or I'd say hot concentrated acidic KMnO4. Okay, hot concentrated acidic KMnO4, right? I think you understand. Hot, it should be hot, it should be concentrated, the medium should be acidic medium, and I have to use KMnO4. Okay, right. So people, it's very, very simple to understand this. Okay, now when we go for ozonolysis, what we do? We actually break this double bond to form oxygen, and oxygen put here, right? When you go for ozonolysis, here also we'll do almost the same thing, right? But what you have to understand is, people, right? This KMnO4 is a very strong oxidizing agent, right? This KMnO4 is a very strong oxidizing agent. Okay, so what it can oxidize? If at all we have an aldehyde, right? If it undergoes oxidation, it is going to form acid. Okay, it is going to form carboxylic acid. Okay, but ketones, if you have, for example, if you have ketones, if you get, obviously when I go for ozonolysis, either aldehyde or ketone will be the product. Okay, so if at all you form aldehyde, you have to oxidize it to acid, right? But ketone, you will keep it as such, because ketones cannot be further oxidized. Okay, now look at this reaction, people. Say if at all you will again learn this reaction in 12th class, but again it's giving you a quick introduction to this. Okay, this is an oxidation reaction. RCHO, that is your aldehydes, on oxidation, right, will always give us RCOOH. For example, if you have CH3CHO on oxidation, say KMnO4, if you keep, right, this is going to form CH3COOH. Say I have this one with CHO here, right? Now again KMnO4, if you do, you are going to get COOH like this. Okay, now this oxidation you have to know for this reaction to happen. Ketones, if you want, just keep it as such. Okay, now all I'm trying to do is that we are actually going for almost ozonolysis only. Okay, we'll break the double bond, put oxygen, oxygen. Okay, here we'll put oxygen, here we'll put oxygen. But if any of these two are going to form an aldehyde, that alone has to be converted into an acid, and the ketone, whatever it is formed, it will be kept as such. Right now, like directly, let me give you an example. Right, say for example, if we had CH2 double bond CH2, KMnO4. If it is KMnO4, it is hot, concentrated, acidic KMnO4. We'll write H plus, acidic. Okay. Now what we are going to do? Break this double bond, put oxygen, oxygen. all we are going to get is what? HCHO plus HCHO, right? Both are aldehydes, right? Now we have to oxidize them, right? We have to oxidize because they are aldehydes to form HCOOH plus HCOOH, right? Now, if at all I take a case where I have an aldehyde and a ketone getting formed, say for example, CH3, CH3, double bond, CH3, something like this, and we go for again same thing, hot, concentrated, KMnO4, right? What are we going to do? Break this double bond, put oxygen. So what is going to form? This particular part would be CH3, C double bond O CH3. This is untouched because it's a ketone, right? But look at this part. This part would be CH3, CHO, and this part alone will get oxidized. When I put this symbol, it is oxidation, okay? When I put oxygen in bracket, it is oxidation symbol, okay? Now this is going to get formed, and this is going to get converted into CH3COOH. So these two are the final products when I go for this particular reaction, right? Very, 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 very similar to ozonolysis, except that if you form an aldehyde, convert that into a carboxylic acid. That is the only difference here. Okay, right? Again, I repeat, exactly like ozonolysis, if you have ketone, convert into carboxylic acid. Sorry. If you have an aldehyde, convert it into carboxylic acid. If you form a ketone, keep it as such. Okay, I hope everybody is understanding what exactly is happening here. Right? I can take humpty number of examples, people. Say, okay, now for example, if I have, okay, this one will be very, only ketone will be formed. Say, for example, if I have this particular double bond and we go for hot concentrated KMnO4. So we'll put oxygen. So what are we expecting? This one is going to form CHO, CH2, 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 four times CH2, right? CHO, CH2, 4 times. Again, this particular carbon again is going to form CHO. But again, this will not be the product. This will get oxidized to form what? COOH, CH2, 4 times COOH. Okay, right? These are the different examples you can have for this particular reaction. Okay, yeah, tell me.
So why doesn't it add in the ketone?
Why does it? Okay, ketones cannot be further oxidized. We have to understand that if at all aldehyde is there, RCO or CHO is there, this is terminal functional group. Okay, only at the terminal ends this will come. That can be converted into an oxidized terminal functional group, RCO, again terminal, right? But ketone, if you have, for example, this one, this cannot be further oxidized because this carbon has been in between. How do you form a COH in between? Not possible at all, because C double bond O OH already three bonds are satisfied. So this can come only at the end. This is the only possibility. You cannot have COOH in between. Not possible at all.
Okay, sir.
Right? Fine. So that is what we need to understand in this question. And there is one more. I don't know whether that is there in your syllabus, but same by just altering this particular condition, hot, concentrated, acidic, right? If I just put cold, dilute, alkaline. What is alkaline? Basic medium. Okay. Instead of hot, concentrated, acidic KMnO4, if we go for cold, dilute, alkaline KMnO4, what is going to be the product? The product is going to be different. Okay. So let me see that also. Right? Oxidation of alkenes only, right? With cold, dilute, alkaline KMnO4. Okay, and again there is a name to this. Okay, that doesn't have a name, but this has a name. Cold, dilute, alkaline KMnO4. This particular reagent is what is called as Bayer's reagent. Okay, Bayer's reagent. Like I even ask, alkenes on round reaction with Bayer's reagent. Bayer's reagent is what? Cold alkaline cold dilute alkaline KMnO4. Okay, so people, it's very, very simple to understand. Okay, C double bond C is there. Okay, and then we have to go for Bayer's reagent. I'll directly write it. Bayer's reagent. Okay, now what is going to happen is it's very simple to understand, people. Now this is what is going to happen. Okay, now look at this. C, let me put this as a dotted line. Okay, now MnO4's structure will actually look like this. O minus, double bond O. Double bond O. Okay, let me write this properly. Okay, so Mn, one oxygen with a negative charge, and one double bond O, another double bond O, another double bond O. This is what is structure of MnO4 minus. KMnO4, it is like this does Mk plus MnO4 minus, right? So what are you going to do is that instead of putting the double bond and the negative charge like this, right? I'll just take out this negative charge and this thing, and I will put this as a resonance hybrid because this can also undergo in resonance. Okay, so there is a dotted line here. There is a dotted line here. So now there is going to be some kind of interaction between this carbon and this oxygen and this carbon and this oxygen. And what you do is that you break this and put H and H like this, right? So if you look at the product, right, the product would have been one OH here, right, another OH here, plus the product. Now this particular part would be MnO2. You can ask me where the H plus or where the hydrogen is coming from. We still have water. Okay, from there the hydrogen is coming. Okay, if you do not understand the mechanism, all we have to understand is you are going for formation of a vicinal diol. Vicinal diol. So you are going to have one OH and another OH like this if you go for Bayer's reagent. And this is the mechanism. Mechanism is very simple. Okay, MnO4 minus resonance hybrid. This resonance hybrid, carbon oxygen bond, add a hydrogen to the oxygen. That's it. Very simple. Okay, right? Say if I give you maybe a perfect, yeah, tell me.
It's KMnO4, right?
Yeah, KMnO4, yes. But we are here taking MnO4 minus. K plus MnO4 minus. That is what is potassium permanganate, right?
So then what happens to potassium?
Potassium will be there. But actually, this one will actually form a complex, okay? We will actually form KMnO2. Potassium, it is called what? Manganate. Potassium manganate will be the product. Potassium manganate will be the product. This will go along with this. Okay, don't worry about the side product. All we have to understand is that we are going to form this particular diol as the product, right? Say for example, if we have CH2 double bond CH2, right? And then I go for Bayer's reagent, right? What are we going to form? CH2 OH, CH2 OH, right? Say for example, if you have a double bond like this and we go for Bayer's, right? What are we going to form? We are going to form one OH like this and another OH like this.
Sir?
Yeah, tell me.
Sir, is this only applicable for alkenes?
What, Kanna? I'm not able to hear you. What is it?
Is this only applicable for alkenes?
Yeah, only applicable for alkenes, yes. Okay, only alkenes can do this.
So if it is done with alkyne, no reaction would take place.
Alkyne's reaction would happen, but again, too much higher level. Even it is not there even for in the case of JE advanced. Maybe if you go to maybe BSc level chemistry, at that time you will learn. But to answer your question, yes, alkynes can also undergo this kind of reaction, but the product will be different. Okay, and don't worry about it. For now, alkenes, cold alkaline dilute KMnO4 diol will be formed, right? And the same alkene with hot concentrated KMnO4, if it is there, aldehydes, no, acids or ketones will be the product. That is all you have to understand. I don't even think that this reaction is there in the syllabus, but you can just not know this. Just by tweaking the conditions, right? This is going to happen. All right. Okay, people. So this is all I wanted to tell. Okay. I don't know how much we'll be able to solve the question. I mean the DPT. Anyway, so try to solve how much ever possible. Okay. Right. A gas decolorized by KMnO4 solution, but gives no precipitate with ammoniacal cuprous chloride. Oh, God. Ammoniacal cuprous chloride, not in a syllabus. Okay, this is not a Stollen's reagent, right? Don't worry about it. Right, this is not in a syllabus yet. Okay, you don't know this. Ammoniacal cuprous chloride is nothing but Stollen's reagent. It's called Stollen's reagent. It is actually a test for aldehydes. Okay, so like if I give you a test tube, right, and ask you to confirm what is the functional group present in this test tube. Okay, there are some tests like this Stollen's test, Felling's test, zinc sulfide, something tests are there that is not yet taught to you. It will come only in 12 plus to you. Don't worry about the first question, right? Fine. Next, benzene reacts with acetyl chloride. Now, what is acetyl chloride? I told you acetyl group is the CH3CO group, right? Chloride is Cl. in the presence of AlCl3 is very simple. We are going to form CH3. No. We are going to form C double bond O CH3. Right now, what I tell you? This is aceto. What is this? I told you the name of this compound also. This is aceto, and what is this? Phenone, right? Acetophenone is what is the answer to this question. A is the answer. Very simple. This is Friedel-Crafts acylation. This question, right? Next, presence of nitro group in the benzene ring deactivates the benzene ring towards electrophilic substitution. Absolutely, because NO2 group is a deactivating group. Okay, activates the ring to electrophilic. No. It enters the ring basic, nothing. Deactivate the benzene towards nucleophilic substitution reaction. No, it is electrophilic substitution. A is the answer. Next, arrange the following highlights in the order of decreasing reactivity from propene. Basically, they're asking about CH3, CH double bond CH2 in the presence of HX is going to form what? Markovnikov's rule, right? CH3, CHX, CH3, right? We have already seen this question, right? Say this HX bond weaker the bond, right? Faster the reaction. Yeah, so it would be HI, HBr, HI. Yes, absolutely. HI is the weakest bond, HCl is the strongest bond. Very simple. Okay, next. What product is obtained by heating?
Can you repeat?
Okay, now ethylidene dichloride. Okay, I forgot to tell you. Ethylidene chloride means ethylidene dichloride. CH2Cl, CH2Cl with 2 times alcoholic KOH. They didn't mention this, but it's 2 times alcoholic KOH, right? 2 times alcoholic KOH. Cl from this, H from this, Cl from this, H from this. CH triple bond CH. That is nothing but ethyne. A is the answer. Okay, next. An aqueous solution of compound A gives ethane on electrolysis. Electrolysis Coles. Right? We are telling that we are forming what? Ethane. Right? So I should have had only 1 carbon atom in the carboxylic acid because it is getting doubled. We are getting electrolysis. So what should have been the acid? It should have been HCOOH reacting with NaOH to form HCOO minus Na plus. Now what will happen? We will okay, we need to go for carbox. Okay, 1 more carbon atom.
CH3.
Yes, absolutely. Yes. Right. So we should have actually gone for CH3COO minus Na plus, right? And minus 1 electron to form, or say 2 moles of this, 2 moles of this will form 2 moles of CH3CO dot. From this minus 2 CO2 molecule to form 2 CH3 dot, so making the bond together to form CH3. So it should have been what? Sodium acetate. This ion is what is called as acetate ion. Sodium acetate. B is the answer to form ethane as the product. Okay. Sodium acetate is correct. Yeah. Right. Next. Which of the following statements are false for benzene? Okay. Electrophilic substitution reaction result in yielding the corresponding mono derivative of benzene. Electrophilic reaction results in the yielding of mono derivative of benzene. Means I can have 1 substituent on the benzene ring. Okay, fine. Bond length between each of the carbon atom is 133 picometer. The bond angle between each carbon atom is 120. Yeah, 120 I can understand because it is sp2 hybridized, trigonal planar, 120 degree. Heat of hydrogenation of benzene is lesser than a theoretical value. Heat of hydrogenation of benzene is lesser than that of theoretical value. It is true. Okay. Right now, what are they trying to say is that what is heat of hydrogenation? See, when you have a C double bond C, okay, and I go for H2, right? So what is going to form? We're going to form CH bond, right? Now, obviously, you understand that some kind of energy will be released during the reaction. This is an exothermic reaction plus some amount of heat will be released. This is an exothermic reaction. Right, because the CH bond is getting formed. Okay, now this heat released is what is called as heat of hydrogenation. Okay, this heat revolved is what is called as heat of hydrogenation. Okay, so what you have to understand is the more stable the alkene, I'll say the stability of the alkene. 1 second, guys. 1 second. Okay, fine. So the stability of the alkene, right, is directly proportional to the heat of hydrogenation. That's what you have to understand. Okay, more and more stable this alkene is, if it undergoes hydrogenation, lot of heat is produced. Okay, right. So now look at benzene. Actually, you should again study this only in thermodynamics, but We go for this. Okay. So now when I go for say 3 moles of H2, right, and we get cyclohexane, right, plus some amount of heat energy. Okay. Now we expect one value of heat energy. Okay, right, but that value is lesser than the theoretical value. Lesser than the theoretical value. You know why? Right? Because whenever we calculate this heat, right, we do not take into account of resonance. Okay, this we know that this benzene thing can involve in resonance, right? So this hydrogenation becomes little more difficult. Okay, and since it is becoming more difficult, little less amount of energy is released because the theoretical value is very high. Theoretical value is less. Okay, theoretical value is high because we are not considering the resonance energy because it's involving resonance, right? So the expected value is actually the observed value is lesser than what we expect. Why? Because you'll study this in depth in thermodynamics. I don't want to go into details as such, right? So what happens here is that because we are not taking into account of resonance when you go for theoretical calculation, that is why the reason is the observed value is lesser than the theoretical value. That's all you understand, right? So this value is true. Okay, where is it? Okay, this is true. Okay, they're asking which is false. The bond angle is correct. 120 is true. The electrophilic substitution reaction results in yielding the corresponding. What do you mean by mono derivative of benzene?
Sir, actually B is wrong, sir. It's not 133.
Yeah, I think some value. This kind of question, very bad question, I would say, because this kind of values, I don't think you have to remember anything. Okay. Sir, now what you have to understand is the bond length of each of the carbon atom to carbon atom is 133. Say, I think the C single bond C is around 141 picometers, but C double bond C is around 120 picometers. Okay. Because obviously double bond is stronger, single bond is weaker. But I know in benzene ring, what is happening? It is neither a double bond nor a single bond because resonance is happening. Right? So it should be in between this. I'm not sure. What is the exact value? Is someone, what is the exact value for C, the carbon-carbon bond length in benzene?
Sir, C double bond C is 134, sir. And C single bond C is 154.
154.
So it would come around 139.
Yeah, approximately the average of this, right? 139 is not 133. So yeah, this is the correct answer. But again, a very stupid question. Okay, you do not have to remember any of these values. Please don't remember anything. Okay, next. Fine. Alkyl halides reacts with dialkyl copper. This reaction, is this reaction even there in textbook, people? Dialkyl copper reagents. Alkyl halides on reaction with dialkyl copper. Do you even have this term Grignard reagent? Do you have that? Did you study in the textbook?
Yes, sir. Somewhere I saw it.
Grignard reagent you saw? Okay. Guys.
So 1 minute, sir, I check.
Yeah. So even if it is there, we'll not spend time on that because again, Grignard reagent is a very important compound. Okay. But I'll make sure for the test which you're going to writing on Sunday, you are not going to get any question from Grignard reagent, even if it is there. But don't worry, we will cover this. Next class, we'll try to cover it. Okay. Right. Fine. We'll go to the next question. This dialkyl copper, Grignard reagent, all these similar kind of reagents. Okay. Fine. Next. 2-methyl butane on reaction with bromine in the presence of sunlight. This is what? 2-methyl butane. 2-methyl butane. This is what is 2-methyl butane, right? On reacting with Br2 in the presence of HNu, we said that Br2 is more selective. So it is actually going to obstruct a carbon atom. I mean, hydrogen atom is going to form the most stable carbon free radical. That would be this carbon, tertiary, right? So we will actually form C, Br, CH3, CH2, CH3 as the major product. Mainly they're asking. That means
option
product.
C, sir.
Right? So it's going to be 2-bromo, 2-methyl, 2-bromo, 2-methyl butane. Yeah, C is the answer. Next. Which conformation of ethane has the lowest potential energy? It's very simple, people. Potential energy is inversely proportional to stability. High energy means less stability. Right? So whichever has the highest stability will have the lowest potential energy. That will be staggered, right? Staggered will have, yeah, staggered. Eclipse will be having higher repulsions. Staggered will have no repulsion. So that is going to be the answer. Right? Next. Arrange the following alkyl halides on decreasing order of beta elimination reaction with alcoholic KOH. So people here, all you have to understand is carbocation formation is there. Okay. So more stable the carbocation, more will be the stability. But whether they have to mention it as either E1 or E2. Say if I tell that A is the most reactive, then it should be say C and then B, right? So it should be A, C, B. Yeah, A is done. B is the answer. Okay, guys, please look at this. So if I just, oh, no. This is plus, this is plus, and this is plus.
Correct, sir.
Yeah, that's the carbocation formation, right? This will be more electron donating, only one, and this is a bigger electron donating group, so decrease in charge. Yeah, B is the answer. Okay, right. Next, and the bond angle deviation in cyclobutane. It is, see, all you have to understand is, I don't know whether you remember this, when we went for conformational isomers, right? We actually studied this in case of cyclic structures. Okay, so we generally write cyclic cyclohexane like this, right? Normal to a planar structure, but it's actually not going to be like this. It is going to be something like this. Okay, a boat structure. No, this is chair structure, right? And why is this happening is because we understood that, say, the bond angle should be 109 degree 5 minutes. All the carbon atoms are sp3 hybridized, right? So we expect the bond angle to be 109 degree 5 minutes, but it will not be like that, because, for example, if you check in cyclobutane, the angle is 90 degrees. Okay, the angle is 90 degree, no way close to 109 degree 5 minutes, right? So that is the reason why in this case also it will be little close to 109 degree 5 minutes, but still you cannot avoid this kind of CC single bond rotations happening. We know CC single bonds can rotate, right? Okay, so anyways, what is the answer? 109 degree 5 minutes should have been the value, but in cyclobutane, what is the value? Only 90 degrees. So I think what is 109 approximately minus 90? How much it will be? 19 degrees approximately. Where do you have? Yeah, 19 degree 5 minutes. Yeah, perfect answer is there. 0.5. C is the answer. Okay. Right. Next, arrange the following carbanions in the decreasing order of the stability. Now we know that this is an sp hybridized carbon atom. This is decreased, right? But I have an electron donating group also in the form of methyl group, right? But in this case, only sp hybridized carbon atom increase only is happening. Sorry, decrease only is happening, and there's no donation, right? And in this case, what we have is CH3, CH2 minus, which is going to increase the negative charge. This is the least stable one, right? This is the least stable one. All right. And then, okay, so obviously C should be the least stable. Where do you have C to be least stable? Either option A or option B, right? And among A and B, which is going to be more stable? Obviously B, because here in this case A has an electron donating group, which will increase the negative charge also. So it should be C, then A, then C. I mean, what is it? C must be the least, then it should be A, and then should be A is the answer to this question. Okay, right? Next, the increasing order of reduction of alkyl halides with zinc and dilute HCl. Zinc and dilute HCl? This reaction is not there for you. Don't worry.
Sir, it's actually there, sir.
It's actually there.
Yes, sir, in the textbook it's given.
Reduction of alkyl halides with zinc and dilute HCl. Dilute HCl, is it going to form RH?
1 minute.
Is it going to form an alkyl halide?
Sir, it gives alkane.
Alkane,
Yes,
that's what. So for example, people, again, okay, this is again a complex mechanism, but all you have to understand is, people, say if you have CH3H and I go for this zinc in the presence of HCl, all you have to do is that H will get replaced with the help and Cl, right? So all you have to get is CH3H, which is nothing but CH4. Okay, but anyways, it's very simple to understand that, again, the CC, whichever bond I can break easily, that is the one who is going to react the fastest. So obviously Ci bond is the weakest, that is going to react the fastest. So A should be the answer to this question. Okay, fine.
Sir?
Next, yeah, tell me.
Sir, similar to this question, we saw another question about reactivity, right?
Yeah, that is about HI. That is about HI.
Can you repeat that?
Yeah, that is very simple, right? So that is about what? That is about C double bond C reacting with HX. right? HX. Again, I can easily break this bond, more will be the reactivity. So HI will be the HI bond is the weakest, that will be more reactive than HPR, than HCl, than HF is the strongest bond. That's it, as simple as that. Here it is about the CX bond, CCl, CBr, Ci, and CF. That is also the same criteria. Easily I can break the bond, easily the reaction will happen. Very simple.
Sir, but then actually you told like if a compound is more stable, then that would be more reactive. So here,
No, exactly opposite. If the compound is very highly stable, why will it react? It's already stable, right? What you have to understand is if the intermediate formed is very stable, carbocation is an intermediate. If that formed is more stable, then easily I can form the intermediate, so the easily I can go to the product formation. There's a difference. Talking about the stability of the reactant itself, that means the reactivity is less. Stability high means reactivity is less. But if the intermediate stability is very high, that means the reactivity of the compound is very high. Are you able to understand?
sir, here what is the intermediate?
Which one in this case?
Yes, sir.
In this case, carbocation is the intermediate. Right? See, you can talk in terms of two ways of reactivity. One, if I give you different alkenes, then you will decide based on the stability of the carbocation form. Right? And if I give you HX different things, HCl, HBr, HX, then you will decide in terms of bond strength. If the weaker the bond, easily I can break that reaction will happen like that. So two kinds of reactivities we can talk. One with respect to alkene, one with respect to HX.
Okay,
Yes?
sir.
Right? Okay. Fine. So that's done. What is Bayer's reagent? We already saw. It is alkaline KMnO4. We saw that. The OH, miscible and diol is going to get formed. Okay. Next, I want to synthesize 3-octane, right? Subsequent circular reaction of sodium amide with an alkyne, bromoalkane, everything is there. What is the bromoalkane? Another alkane. It's very simple, people. All you have to remember is alkyne forming a reaction with sodium to form the negative charge, nucleophilic substitution. Now all that we have to form is oct3ine or 3-octane. How will we write? CH3, CH2, C triple bond C, CH2, CH2, CH3, correct? 1, 2, 3, 4, 1, 2, 3, 4. Oct3ine, right? Now people, it's very easy to understand. This should have been the negative charge and here should have been the bromine or chlorine or whatever it is. Only then the reaction will happen. Look at this. CH3, CH2, C triple bond C minus Na plus, and look at this one. Say I have CH2, Br, CH2, CH3. Now look at the reaction. This is going to come and this is going to break, and you eventually are going to form what? This particular product. Very, very simple. Okay. So I should have had this one, that is this one, right? And I should have had what? 3 carbon atom with Br. Yeah, A is the answer. Simply I can tell. Very easy. Okay, right? Next, in the following sequence of reaction, the alkene is converted into product B. Okay, this is the alkene, ozonolysis, and then everything is ozonolysis only. A and B are not required. Directly break this bond, put oxygen. So we will form CH3CHO plus CH3CHO. Done. B is the answer. 2 moles in the same. Yeah, tell me.
Sir, so that sodium amide is same as the soda amide.
Yeah, okay. So in this case, they're telling soda amide, right? Soda amide is going to be a very strong base. Very, very strong base. Soda amide is very simple. NaNH2 is what is soda amide. Same thing. So if at all I have CH triple bond CH reacting with soda amide, that is NaNH2, same thing is going to happen. CH triple bond C minus Na plus. Same thing will happen. Acid base reaction. Okay. Right. Next. Toluene reacts in the presence of chlorine of light. Be very careful. Just because you're seeing toluene, chlorine, do not go for electrophilic substitution. Look at this very carefully. Chlorine in the presence of light means what? We have benzene ring with
free radical substitution.
Free radical substitution. So chlorine in the presence of sunlight, H nu. What is going to happen? We cannot displace any one of the hydrogen atom here because all of them are sp2 hybridized. I can remove only one of this, right? So we would have formed CH2Cl. That's it. Okay. Now this particular group, right? The CH2 with CH2 is what is called as benzyl group, right? And since it is chlorine is there, it is going to be called as benzyl chloride. Remember, C6H5CH2 is what is called as benzyl group. Okay, and along with it, whatever is there, that particular this thing, benzyl alcohol, benzyl chloride, something like that. Okay, instead of in benzyl alcohol, I would have added OH here, C6H5 CH2OH. Okay, so benzyl chloride is what is the answer to this question.
Sir, then what is benzoyl chloride?
Okay, benzoyl chloride is very simple. Benzoyl would be C double bond O with a CF. Okay, this group is benzoyl group. Okay, with the chlorine. Okay, this is benzoyl chloride. Okay, right? So that's the answer. Next to the following reactions will yield 2,2 dibromopropane. We need to get 2. See, look at this. 2,2 dibromopropane. How do we write? Br, CH3, CH3. Right? Now we have, it is like very simple, right? We have to go for 2 bromines, right? But remember that if at all we go for Br2 addition, what is going to happen? We are going to get vicinal bromide. For example, people, if I had CH2 double bond CH2, if you can remember the cyclic bromonium ion reaction in the presence of CCl4, what are you going to get? CH2Br here and CH2Br here, right? This we cannot do because we want to get vicinal dihalide. We have to go for Markovnikov's addition. Very simple. We have to take an alkyne and then go for what is that? And then go for HBr addition 2 times. Right, so see where is alkyne? Alkyne is here, and 2 moles of HBr absolutely in this carbon only. Both the bromine atoms will come. 2 times Markovnikov's. Right, so definitely C is the answer to this question.
Sir,
okay.
Instead of 2, if it was 1, then only 1. Yes, sir. 1 HBr.
1,1 dibromopropane.
No, sir. I'm asking if in case it was CH3, CH plus 2. Instead of 2 HBr, 1 HBr.
Only 1 HBr means the product will be like this. CH3, CBr, double bond CH2, like this.
Sir, so this compound is neither vicinal nor geminal.
Yeah, obviously, we can go for vicinal or geminal only if you have di compound. Di do functional groups will be there.
Okay, sir.
Understood, right? Okay, next. Really this one? Okay, fine. Anyways. The addition of HBr to butane gives a mixture of product ABC. Butanene. Guys, I'll be back in a minute. 1 second, I'll be back. Okay, people. So what I was trying to say is, but C2H5CH3, C2H5CH3, this is optical isomerism. Okay, this question is from optical isomerism, which you will study only in 12th class. Okay, I don't have time to go through this because this will itself take some 3 hours of my class. Okay, optical isomerism itself. I don't want to go through this. Don't worry about it. You are not going to get questions like that in your school exams as well as in your tomorrow and your external exam. Yes, what was the question?
Sir, actually A and B both are major, sir.
A and B both are?
Both of them are going to be major, sir.
A and B, both of them are going to be major. Yeah, that we can tell. Yes, right? Because you understand that it is Markovnikov's, right? HBr, if I go, it is going to be Markovnikov's. This is anti-Markovnikov's product, minus product. Both of the things you understand it is Markovnikov if you understand properly. Okay, but these two are actually what are called as optically active compounds. Okay, optically active compounds. Okay, anyways, we can write the answer. A and B are major and C is the minor product. Very, very simple. Markovnikov's rule. Okay, but exactly between A and B, both of them will have equal amounts. And what are these two? These are optical isomers. Okay, these two are optical isomers. Don't worry about it. Next, 1 mole of symmetrical alkene. Whenever we go for symmetrical alkene ozonolysis, we know we are going to get an alkene, an aldehyde, isn't it? Now all the alkene is having molecular formula of 44U. The aldehyde formed is having a molecular formula of 44U. Okay, right. So we can actually neglect certain things. Propene is not a symmetrical alkene, right? Because it looks like this. Okay, it's not symmetrical. Doggone. But-1-ene again is not symmetrical, right? But but-2-ene and ethene are symmetrical. Okay, right. But-2-ene, how do we write? CH double bond CH, something like this. CH3, something like this. Now go for ozonolysis. What are we going to form is CH3CHO. Calculate the molecular mass of this 2 carbons, 24 plus 4 hydrogens, 4 plus 1 oxygen, 16. How much? 40, 44. Yeah, this is the answer. That's it. 2 butane is the answer to this question. Okay, next. Acetylene. Acetylene is CH triple bond CH. Okay, acetylene is prepared by action of water on CaC2. I think this was one of the reaction we didn't see. I asked you to study, right? CaC2 is the reaction, right? If you want to understand what is CaC2, CaC2 is like this: C triple bond C minus minus, right? And we'll have Ca2 plus. That's it. This is what is called as CaC2 minus. Obviously, if I replace both of these with H and H, then we are going to get CH triple bond CH. Okay, right? Very simple. Next, pyrolysis of coal with heavy oil in the presence of H2. Now remember, heavy oil is nothing but hydrocarbons, right? Hydrocarbons. I know hydrocarbons on heating with carbon oxygen will always form what? CO2 plus H2O. Very simple, right? So a mixture of low boiling. Oh, it's pyrolysis. I'm so sorry, not combustion, people. I'm so sorry. This is combustion, right? So heavy oil is going to be having a lot of carbon atoms. So it is going to form what? A mixture of low boiling carbon atoms. That's it. So many hydrocarbons will be formed because pyrolysis, right? What is pyrolysis? A big compound getting decomposed into smaller compounds, smaller alkanes. Very simple. A mixture of low boiling hydrocarbons is what you will get. What is low boiling? They will have lower boiling points. That's what you understand. Okay. Next, N-propyl bromide. N-propyl means normal propyl. Okay. CH3, CH2, CH2, Cl. On reaction with alcoholic KOH. Very simple. H from this, Cl from this.
Sir, 2 alcoholic KOH.
Why 2 alcoholic KOH?
Ethanol.
No, the answer only, they didn't mention anything with respect to the number of moles. N-propyl bromide is this, so Br, sorry, this is not Cl, Br with alcoholic KOH, Br from this, H from this, double bond, that's it. So answer should be propene A. Okay, right? Fine, next question. The following reaction is, this is very simple reaction. What is happening? You do not have this reaction. But again, it's very simple to answer this question. Okay, what is happening? Br is replaced with OH. What kind of reaction is this? Substitution reaction, or little more specifically, I can tell that it is actually going to be a nucleophilic substitution reaction. Right? OH minus replacing Br minus. Right? But it's not in your syllabus, but still you can know this. Very simple. Next, ethyl benzene can be prepared by Wood's reaction. Can we prepare it with Wood's reaction? No, we can prepare it.
Sir, cannot be prepared.
Yeah, it cannot be prepared because it is having 8 carbon atoms, but still you can have only aliphatic groups. In Wood's reaction, we can go for only aliphatic hydrocarbons. Right? We cannot go for this thing. So it is going to be Friedel graphs. How do we do Friedel graphs? When we go for benzene with CH3, CH2, Cl in the presence of AlCl3. Now what are we going to form? CH2, CH3, ethyl benzene. Right? So Friedel graph reaction is the answer to this question.
Sir, okay. It's actually which cannot be prepared.
Oh, it cannot be prepared by Wood's reaction. But Clemmensen reaction, you don't know. Wood's fatigue. Do you have fatigue reaction also in your textbook? Do you have fatigue reaction? Wood's fatigue is different. Fatigue alone is different. Do you have fatigue reaction? Check.
No, sir, I don't think so.
Sir,
All right.
it comes under alkene or?
It comes under preparation of alkanes.
No, sir, it's not there.
Not there, right? Don't then leave it. This question is this thing. So you cannot prepare the Woods reaction, okay? Because you can do only aliphatic hydrocarbons, not aromatic hydrocarbons in Woods reaction. Okay, Clemmensen reaction you don't know yet. Clemmensen reaction I can tell you what is going to happen, but again I don't want to really confuse you. Okay, don't worry about it. Again, this is coming 12th class. You'll study. Right. Next, what does marsh mainly contain? It's very simple root, CH4. Right. I don't know whether you've seen this movie. Tamilukku en ondrai eluthavum. Have you seen this movie? Tamil movie it is. Okay, he'll actually go to the marsh and actually he'll collect methane gas. From methane, he'll try to create some fuel in that particular movie. Okay, marsh is what? That marshy land, that Sagadi, we tell in Tamil. I don't know how many of you understand. Right, marshy land. That's the exact word in English. I don't know. I don't know. I don't either line other language. In Tamil, I know it's called Sere, like Sagadi. Right, that kind of land. It's only going to be CH4. Okay, right. Next, the correct IUPAC name. I think you should be able to do this, right? Right. This group is what is called as isopropyl group. Okay, so this is going to have more priority. So 1, 2, 3 isopropyl and 1, 2, 3, 4, 5, 6. 6 ethyl and totally 8 carbon atoms. A directly you can tell A is the answer, right? Again, this is Grignard reagent. Okay, this I will teach you. Don't worry about this. This is Grignard, and don't worry, questions are not going to come. Even if it is going to come, I'll give you the mark to that. Okay, because there are so many reactions. You are seeing how many classes it is taking for each and every reaction, how much time it's taking. Okay, so I hope you understand. This we'll see again in the next class. Whenever we have the next class, I'll just I can have a very good discussion about Grignard reagent alone, right? For like say half an hour, 1 hour, we can have very important reagent. Okay, we'll see this. Right. Next, among the following compounds, the one that is most reactive towards electrophilic substitution. Now we know nitrobenzene deactivating, benzene, okay, benzoic acid COOH, again that is deactivating, right? But toluene CH3 is activating. So C is the answer, most reactive. Okay, next, the peroxide effect. We have seen anti-Markovnikov in the presence of HBr in non-symmetrical alkene involves a free radical mechanism. Homolytic fission of the double bond. Homolytic fission of the double bond. Homolytic fission happens there. Ionic mechanism obviously no. Heterolytic fission obviously no. Free radical mechanism is obviously correct, but homolytic fission of the double bond.
Sir, it's heterolytic fission of double.
That does not happen here. What happens? First, the Br dot comes from the HBr. Okay, and this is eventually going to this. Actually, you can show this pi bond undergoing homolytic cleavage, but it is not going to be exactly like the moment it is going to come from. It is going to get attacked. It is going to come and attack. Okay, but again, a stupid question because both of them are correct. Okay, free radical mechanism absolutely right. Homolytic fission of the double bond, yeah, we can tell. But I would say if at all this question comes in exam, what answer I will choose? I will choose only free radical mechanism. Okay, but again, theoretically speaking, both are correct. Okay, but the best answer here would be free radical mechanism and not this, because this is not exactly happening. Hope you understand what I'm trying to say. Okay, fine. Next, the most unlikely representation, of resonance structure of para-nitrophenoxide. Joe, you don't know what is phenol also. People, phenol is this. Okay, benzene ring with alcohol is what is called as phenol. Phenoxide is very simple. You have to remove a H plus from this. This is going to become phenoxide. Okay. Now para-nitrophenoxide is very simple. NO2. Okay. So you can just draw the resonance structure and check for yourself. Okay. Whatever is going to come. Very, very simple. You know how to draw the resonance structure, right? Right. I will leave this question to you.
Sir?
Next. Yeah, tell me.
Sir, actually in this question you can directly say, sir, it's option A because N is having 5 valency.
Yeah, actually, yeah. N is having 5 valency. Good observation, Raghav. Yes, easily we can do. Even though you go for the resonance structure, you can actually tell because N double bond or double bond, but having 5 bonds. Yeah, definitely. It cannot have 5 bonds. Even if it has a positive charge, maximum only 4 bonds. Okay, right? Not 5 bonds are not possible. Okay, next. General formula of cycloalkane. Now, cycloalkanes are, you can understand, ring chain isomerism. Why? Because I can have double bond as well as double bond. So rings will have CN, H2N as similar to alkenes. They will also have CN, H2N. That's it. So C is the answer. Next, HBr reacts with this one in the anhydrous conditions at room temperature. Nothing. This is your Markovnikov's product. This is where you will get Br. So we see CH3. Where are you? CH3, CHBr, or CH3. Yeah, this is the answer. D is the answer. Very simple. Okay.
Why is
Next.
H coming, sir? It should come only CBr, right?
Why we are adding, or what are we adding? HBr we are adding, right? Look at this. We have CH2, CH, OC.
H removes the double bond, and now Br substitutes the remaining CH. So it should come CBr, right?
No. First H plus. Okay. Say
Yes,
this
sir.
bond goes like this, and this comes and attacks here. So we will form what? CH3. Pi bond is broken. CH plus. This carbon is losing electron.
Okay,
Carbocation and CH3. Then comes Br minus to form CH3, CH, Br, OCH.
okay, sir.
Right? Okay. Next, ethene is obtained by electrolyzing ethene. Okay. Oh God. For 11, they are torturing you guys. Okay. Literally, they are literally going to torture you with this kind of questions. Really? This question? Guys, I really did not expect this question coming here. Look at 36th question. 1-bromo, 3-chloro, cyclobutane. We just saw this question and I told you that this question will not be asked. Right? This is Wood's reaction, right? 2 Na molecules in the presence of dry ether. I told you what is going to get formed. D is the answer, right? Okay. Right. Anyways, like really succinic acid, fumaric acid, all these things you have to understand. What is this? Okay, people, what is the time? We really don't have time. How many questions are there? 60 questions are there. Yeah, 60 questions, and how many we completed? We completed only 34. Okay. Guys, can we have another class before you go to the exam? Is it okay for you if I can have a class?
Okay, sir.
Okay, maybe I will speak with Raghav. Okay, I'll speak with Raghav and let you know. Like I'll just tell him that some 25 questions are remaining in the worksheet to be discussed. Right?
But then can you tell out of this 25 which should be attempted, sir? Okay,
later this I can tell you, right? See, don't worry about these kind of questions. It is not, again, this question is gone. Organic compound can be formed by this, and all you can do. Organic compound, okay, this all you can do. The compound formed reduction of oxidation of ethyl benzene. Don't do this. When a branch sign out, okay, this is okay, you can do. Benzene reacts in the presence of sunlight, okay, you can do. Okay, this is not there for you, sorry. Okay, next, dibromo derivative alkene react with sodium metal to form an alicyclic hydrocarbon. Dibromo derivative react to form, okay, this you can do. Wood's reaction. Okay, the product of which product is obtained by passing ethanol vapors over heated alumina. Okay, do this. Just check your books. Okay, this is very easy. And don't do this question. Fumaric acid, you don't know what is this yet. Okay, which of the following will not geometry isomerism? Please do. This also you can do. Then the catalyst required, you can just take this. Okay. Next, this you can do. Hydrocarbon which can react with sodium and liquid ammonia. Yeah, go for it. And propyl bromide with alcoholic AOH. Okay. Hydrogenation is lower most of alkenes. Okay. Next, the result of hydrogenation to isomeric products. Okay. Decarboxylation of this is faster than this. Check this out. Okay. Next, electrolysis on alkene is faster than okay. Lactic acid, don't worry, lactic acid. Alkanes have even number of carbon atoms. Okay. Addition of Br2 to brom, okay, to optical isomers. Don't worry. Don't do this question. Next. Bayer's reagent, whatever. To the following is the most reactive cycloalkane. Okay, which is going to be least stable? Yeah, you can answer this question. Out of this, form addition compound of the distinct order. Right? Cyclopropane, cyclobutane. So some addition compounds. How will they even form addition compounds? Okay, this question is not there. Okay, this question you can do. Next, dash has the greatest bond angle and zero strain energy. Okay, check this out. If the angular deviation is higher, then what will happen to the torsional strain? Do this. SN1 reaction, don't worry. Nothing. This question is not there at all. Bimolecular, that's it. Right? So whatever I've marked wrong, don't do those questions. Whatever I've marked on a tick, you can do those questions. Okay. And I will try to have one more class. Okay. I just need 1 more hour for me to, completely discuss the questions. Right. I know I went a little rushed. Right. I know, I understand. But people, I'm always going to be available online to you. Okay. If at all you're not able to solve a particular question, please don't hesitate. WhatsApp me. I'll be able to help you there. Okay. So I think with this, I'll stop. Right. Anybody has any particular questions?
Okay. Sir, did you set this assignment?
You want this PDF?
Can you give with this tick mark, sir?
Yeah, I can give it. Why not? Yes. Okay. If I send it to you, will you be able to pass it on to everybody?
Yes, sir. I'll do it. Right away.
I'll send you right after the class. Now only I'll send you. Yeah, that is okay. Okay. Any other questions anybody has?
And sir, by the way, did you set this assignment, sir?
Sorry?
Did you set the assignment paper?
No. I will send. But just after I go out of the meeting, I'll send it to you.
No, sir. Set, sir, not send.
No, I did not send this. The question paper you're asking, your test paper.
Yes, sir.
Yeah, I have gone through the questions. I know what questions are there, but not exactly I prepared. Okay, but I know what questions are there. Good question paper. It will make you think. I say all things which I've seen in the class only. But yeah, it will make you think. Nice question paper. You'll enjoy.
Okay, sir.
Okay. Right. Thank you so much, people. We'll meet again very soon. I think you have holidays, but we will try to have a class. But even if you don't have a class, I am always available online to you. You can always text me. Right. I'll be able to help you there. And I think you can have a very happy New Year, very happy Christmas. Celebrate and have a prosperous New Year. Right. And thank you so much. We'll meet again.
Thank you, sir.
Yeah. Thank you.